Okay, welcome to Let's Get to the Marks. We're looking at the AQA GCSE Chemistry Higher Tier Paper 1, 2022. You've got an hour and 45 minutes to do this. You'll find the link in the description. So you might want to open up the page, watch this on your other screen, and you can do the questions and then check the walkthrough. Or you can do whatever you want with it. Use as you see fit. Let's go. So as you can see here, before we get into it, we've got 8 questions. Obviously, this is the PDF taken from the website, which, as I say, the link's in the description for this. So here we go. Let's get into the first question. Question 1. This question is about metals and non-metals. Figure 1 shows an outline of part of the periodic table. Here's figure 1. We got A, we got B, we got C, we got D. 1.1, element Q is a dull solid with a melting point of 44 degrees. Element Q does not conduct electricity. Which section of the periodic table in figure 1 is most likely to contain element Q? Tick one box, A, B, C, or D. Now, hopefully, you'd all go D here. Now, why D? Well, a couple of clues. It's a dull solid. So A, B, and C are metals. All of these here are metals, and they're all going to be shiny, okay? It melts really easy, 44 degrees. I mean, it's barely a solid at room temperature. So it's got a low melting point. That strikes of a non-metal too. Does not conduct electricity. We know that A, B, and C will because they're all metals. All right, let's move on. All right, let's look at, we got question 1.2. Element R forms ions R2+ and R3+. Which section of the periodic table in figure 1 is most likely to contain element R? So the only clue we've got here is that it can be an ion of 2+ or 3+. And there's only one block in the periodic table we find those elements, and that is over here. You probably know these are called the transition metals, and one of their key properties, their chemical properties, is that they have multiple oxidation states, multiple ionic charges. So iron can be +2 or +3, copper can be +2 or +1. So they have different ionic charges. Right, let's check out question 1.3. Give 2 differences between the physical properties of the elements in group 1 and those of the transition elements. Key word here is 2 differences and physical. They don't want chemical properties like, oh, group 1 is really reactive. They don't want anything like that. That's a chemical property. They want physical properties. Transition metals, we could put higher densities. Obviously, you can write the opposite of all of these. Not higher boiling points. That's shorthand for boiling points. Melting points. MPTS, shorthand for melting points. Stronger and harder. Okay. Now you could say the opposite. You could say group 1 has got lower densities, lower melting and boiling points, and is softer. Okay, let's move on. All right, scrolling down. Hopefully you're good with this, the electronic configuration. So 1.4, complete figure 2 to show the electronic structure of an aluminium atom. Use the periodic table. Now, if we get up the periodic table, what we're going to find is that aluminium has 2 numbers, okay? Aluminium has 27. Now, some periodic tables, that's at the top, some it's at the bottom, and it has 13. You should know that this is the atomic number, and the atomic number tells you what? Well, it tells you number, Sugar Ray Leonard, number of protons. It doesn't tell you the number of electrons. However, in a neutral atom, protons equal electrons. So in a neutral atom, which this is, it hasn't called it an ion, and over here it's mentioned the word atom. All atoms are neutral, and that means they have the same number of protons as electrons. So because it has 13 protons, it's going to have 13 electrons. Now we just need to put them onto these rings. So you can use circles or you can use crosses. The inner shell can hold a maximum of 2, and then we put these on. It's best to pair them up, but at GCSE you won't be punished if you don't pair them up. It just makes it a lot easier to count. It's much easier to see that as 2, 8. And then we've got 3 here. And of course, you find aluminium in group 3 because it has 3 electrons in the outer shell, and in period 3 because it has 3 rings. Right, let's move on. Aluminium is a metal. Describe how metals conduct electricity. Answer in terms of electrons. So, a number of key points here. What is it that all metals have that allows them to conduct electricity? And this is only found in metals, and in graphite or graphene has this as well. So they have delocalized electrons. Now, you've probably heard the term free electrons. Now, you can use free electrons at GCSE, but when you get to A level, you can't. So you might want to get, if you're thinking of taking chemistry for A level, you might want to get out the habit of using the word free electrons. They have delocalized electrons. Now, that would score you 1 out of the 3 marks. So what's the next bit with conducting electricity? And anything that conducts electricity can do this. So these free electrons carry charge through, and then the next mark is the structure. Yeah. So you're looking at delocalized electrons can carry charge through the structure. Of course, it's got a giant metallic structure made of positive ions and delocalized electrons. So essentially what you're saying is the electricity, the current and charge can move carried by the delocalized electrons all through the solid metal. You pretty much will get a question about why something conducts electricity in every chemistry exam. So make sure you know the difference between those and how melted ionic substances can conduct electricity. Right, let's go to 1.6. Name the type of bonding in compounds formed between metals and non-metals. So straightforward, this one. It's ionic bonding, always between metal and non-metals. And now we can move, that will score you a lovely mark there. We're nearly 1/8 through the exam because there's only 8 questions. So we're nearly through that first question. Okay, now we've got 1.7. Magnesium oxide is a compound formed from the metal magnesium and the non-metal oxygen. Describe what happens when a magnesium atom reacts with an oxygen atom. You should refer to electrons in your answer. Now, this is a very, very common AQA question. They love to talk about this. Now, I'm just going to draw out magnesium. If you go to the group magnesium's in, it's in group 2, so it has 2 electrons in its last ring. And then if we go to oxygen and we just draw the last ring of oxygen, oxygen's in group 6, so it has 6 electrons. Notice I'm using crosses and dots or circles, and the reason for that is so that I can see where they're going from. What's going to happen when these two get together? I'm sure you all know that these 2 electrons are going to move over here because they want full outer shells. So this is electrons, and they're moving from the magnesium to the oxygen. And that alone is going to get you 3 marks. And what happens afterwards? Well, afterwards, we have an ionic bond formed. Now, you don't need to draw any of this. This is purely just showing you for your understanding of what this question was banging on about. You actually don't need to draw any of this. This is a written answer, not one for diagrams. And so oxygen will have picked up those 2 electrons from magnesium. So, okay. And so what we can say, that's going to get us our 4th mark for describing what they're like after. So we're going to say 2 electrons move from magnesium. Transfer is a better word, but still, you'll get the marks for move. 2 electrons move from magnesium to oxygen. That alone is going to get you 3 marks. Electrons gets you a mark. 2 electrons, spotting the amount, gets you a mark. And from magnesium to oxygen gets you a mark. I know, all those lines, and you can just pack it at 3 marks in a couple of words. Okay, what's the last mark? You're going to be able to say things like, they now have full outer shells. That could get you a mark. We could basically say Mg becomes Mg2 plus, and O becomes O2 minus. So I can give the ionic charges and etc. So one's a positive ion, one's a negative ion, that kind of thing. So I would always write as much as you can on these to try and make sure you get all the marks. They're worth 4 marks and they come up in nearly every chemistry exam every year. All right, let's rock. Okay, question 2. Sodium carbonate reacts with hydrochloric acid in an exothermic reaction, a heat-giving out reaction. The equation for the reaction is Na2CO3 solid plus 2 hydrochloric acid aqueous, arrow, 2 sodium chloride aqueous plus carbon dioxide gaseous plus water liquid. A student investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached by the reaction mixture. So they're changing the mass. So we know that our independent variable, they're changing the mass. And what are they measuring? They're measuring the temperature. And they're trying to find out what happens when we change the mass to the temperature. Plan an investigation to investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached. So what did they do? They're adding this sodium carbonate to acid. So the only thing I want to change is the mass of sodium carbonate. So what I'm going to start with is my independent variable. What are you changing? Whenever you plan an experiment, write down what the independent variable is. You won't get marks for necessarily identifying it as the independent variable, but you need to talk about it. So use different masses of sodium carbonate powder. Now, how am I going to measure out the different masses of sodium carbonate powder? Well, I'm going to using a, you could say, a measuring balance. Using a measuring balance, a scale, a weighing scale, or a yeah, you get the idea. So that's going to score us a lovely mark there. Okay. Now, add the sodium. Whoa. What we're going to do next actually is we're going to take the hydrochloric acid. We want to measure the temperature before we add the sodium chloride. So we need to make sure we use the same amount of acid each time. And when you're using a liquid, you want to use a measuring cylinder to calculate the volume. So use a measuring cylinder to measure out the same volume of hydrochloric acid each time. Now, this is called a control variable. So what you're going to notice is that when they ask you to plan an investigation, most of the marks are going to fall into independent, dependent variable, and then your control variables. So that's one of our control variables. We've stated there, keep them amount of acid the same each time. You could just give them a known amount of acid. You could say, hey, measure out 25 centimeter cubed of acid each time, and that would get you the same marks. Okay, so next thing, take the initial temperature of the acid using a thermometer at eye level. Now, sometimes they say don't worry about safety precautions. I would say wear goggles here. It's probably not in the mark scheme, but you never know. You want to use your measure, look at your thermometer at eye level each time. We could say wear goggles. It won't be in the mark scheme. They haven't asked us to take account of safety. So this is actually what this is part of the dependent variable. Okay. Now we're going to say add the solid, which is the sodium carbonate, to the acid. And how long were we adding it for? Well, add the solid to the acid. We don't need a stopwatch. We can just say are we going to measure the temperature? We could say measure the temperature every minute. Measure the temperature every 10 seconds until the reaction is over. Record the highest temperature reached. So we're really only interested in finding out the highest temperature reached And we can then say, calculate the temperature change, which you do by subtracting the final from the initial. Okay. So this is all part of the dependent variable, what you're measuring and how you're measuring it. Couple of other notes with control variables and things that could affect the experiment. Another control variable is make sure you use the same concentration of hydrochloric acid each time. So a little trick is to make sure that when you're doing a experiment and you've got an acid and you're not changing the acid, then you get 2 marks for saying keep the concentration and keep the volume the same. So that's important. Couple of other things to increase accuracy, use a polystyrene cup, as this will reduce heat losses. So using a polystyrene cup was going to reduce heat losses as it's an insulator. And then, of course, the bit that everybody loves is repeat the investigation and calculate a mean highest, a mean temperature rise. Mean and so that's just like a bonus mark, repeat and calculate a mean. So you can see if you can get all of that down, you're going to pick up all 6 marks. Beautiful. All right, let's move on. And then I'm going to flip back up to the graph in a sec. 2.2, determine the gradient of the line in best fit in figure 3. Use the equation, change in the highest temperature over the change in mass. Give the unit, gradient and unit. Let's have a go. We can, it's a straight line, which means the gradient's going to be the same all the way up. So we could start here. We can start wherever we like. Personally, I like to start somewhere it's easy to measure, like there. So if you see there, that is 2.1. So that's 2.1. And now what we can do is we can go up and across to where it will be nice and easy as well. So I'm going to draw a little box going up like this, up to this line, and then across. Well, why am I doing that? Because it makes this one nice and easy. This is 20 over here. This is 24, and this is 28. So I know that my y-axis is 4. Okay, my y-axis, I've got a difference of 4. Now I want to check my x-axis, which is slightly more difficult because my x-axis, I've got 2.1 and I've gone over here to, that's 4.5, 4.6. So along my x-axis, the change is 2.1 to 4.6. So that's 2.5. What we're going to do now is do y-axis over the x-axis and 4 divided by 2.5, and that equals 1.6. You can pick anywhere you want. The gradient will be the same, but I tried to pick somewhere where my numbers here, like 24 and 28, it's going to be really, I got at least one easy calculation for the y-axis, and then my x-axis was slightly more difficult, but you see, it was all right for my x-axis to be difficult along here, across here, because they were easy to read, because it was 1 square equal 0.1 of a gram, whereas going up, it was slightly harder to calculate. Okay. There's our gradient. Now we need the units. How do you write the units? Well, you want to take the units on the y-axis. And what's the units on the y-axis? It's degrees. Okay, so we're going to write degrees. And then we're going to look at the units on the x-axis because we've got the x underneath. And it's grams. So I want degrees. And what did we do with the degrees? We divided them by the grams. So the units are degrees per grams. Y over X, coolio. Okay, 2.3, the initial temperature of the reaction mixture is where the line of best fit would meet the y-axis. Determine the initial temperature of the reaction mixture, show your working. So once again, the initial temperature is where the line of best fit would go down and meet the y-axis. Determine the initial temperature, show your working. So this is dead easy. We want to find out what was the starting temperature. Well, look, all you do is, I'm going to do this in a different color, but you continue this line on like that. And that gets you 1 mark just for drawing on the graph. So make sure you draw on the graph. And then all you've got to do now, he says, all you got to do is calculate what number goes there. 2's 20, 22, 24. So we know that it's 2 over 10. Each square is worth 0.2. So if I start here at 20 and I go, I've made that really hard to see by putting a bloody pink purple thing there. So we go 20.2, 20.4, 20.6. I think my line, I'm going to go with 20.6. Okay, my line's a bit bent. If I wasn't doing this online, I'd be like that. It'd be there, it'd be about 20.6. So it might be a bit straighter. Is that straighter? Nah, messing about. 20.6 to 20.8, somewhere around there on your graph. Okay, super. And that will get you 2 marks. Just slurping my tea. 2.4, another student repeated the investigation but added sodium carbonate until the sodium carbonate was in excess. What does that mean? That means all the acid had been used up and you only have sodium carbonate left. Which sketch graph shows the results obtained when sodium carbonate was added until in excess? Right, I need to show you all the sketch graphs. So there's actually 3 of them. So we've got A, highest temperature reached by the reaction mixture in C, and the mass of sodium carbonate. So they added it until adding it anymore, it was in excess. So which one of these is going to be the correct answer? Well, what's going to happen once you've added all the sodium carbonate and there's no acid left and you keep adding sodium carbonate? Well, once you've run out of acid and you've got excess sodium carbonate, the reaction's done because one of the reactants has run out. So the only reaction that shows the reaction's done is this one. You can see here, keep adding sodium carbonate, the temperature doesn't change. What does that mean? It means the reaction is done. You've used up all the acid. You can keep adding sodium carbonate, the temperature will not change. Okay, so the answer here is C. We have figure 4 shows a reaction profile for the reaction of sodium carbonate with hydrochloric acid. We have x-axis here, progress of reaction. What do labels X and Y represent on figure 4? And we've got Y. So X is the energy. You can see here the reactants are at higher energy than the products. This is energy on a energy profile diagram. And then what is Y? Well, this is the difference in energy between the reactants and products. So this is the energy change or the overall energy of the reaction. So we can call this the energy change. Okay. And then we have 2.6. How does the reaction profile show the reaction is exothermic? Well, if you look here, afterwards, the products have less energy in them than the reactants. So where did all that energy go? And the idea is that energy, which is Y over there, has gone out to the surroundings and heated the surroundings up, hence the word exothermic. So it's been lost to the surroundings. So the reaction showing that it's exothermic is there is less energy in the products, energy transferred to the surroundings. Okay, so overall we've had or we could say we've had a decrease in energy. So I could say decrease, can't spell, guys, decrease, okay, in energy, or there is less energy in the products as it has been transferred to the surroundings. Cool, hope you did well with that. 3. So this question is about the forms of carbon, or different forms of carbon. They're called allotropes, the different forms of carbon. Figure 5 represents the structure of diamond, carbon atom here. Describe the structure and bonding of diamond. So the key words here, and students miss this all the time, but structure and bonding. Can you name the structure? And can you name the type of bonding in diamond? There's only 2 types of structure in chemistry, and they are giant and simple. So is that a simple structure or a giant structure? The answer is it's a giant structure. So we can say it has a giant structure. We actually often call it giant covalent or macromolecule or giant lattice, but basically the word giant's key. So it has a giant structure. What type of bonding is in non-metals? Carbon is a non-metal. So it has covalent bonding. So you've now just described the structure and the bonding, and you say, hang on a minute, I haven't got 3 marks, I've only got 2. Well, the only other thing we can say about diamond is that each carbon atom, look at this carbon atom here, it's 1, 2, 3, 4 bonds, because it's in group 4, and it's bonded to 4 other carbon atoms. So we want to say each carbon is bonded to 4 other carbon atoms, and that's going to get you the 3rd mark. Let's check out the next question. 3.2, explain why diamond has a very high melting point. Now, some of these points here are relevant to down here, but we need to use a bit of explanation. So what does that giant structure do? The giant structure means there are, keyword, lots of strong covalent bonds. Notice I've mentioned the giant structure again and the covalent bonds. If you've got lots of them, you need lots of energy to break the bonds. So if I want to melt a diamond, I need to break all of those bonds. So it's the fact that there's lots of them. If there was just one covalent bond to break, that's not a lot of energy, but there were trillions and trillions and trillions of covalent bonds in a diamond. It's got a giant interlocking structure. We just call it a giant structure. Lots of strong covalent bonds, lots of energy needed to break the bonds. So that's going to get me 3 marks, 1 for the word giant, 1 for the strong bonds, and 1 for lots of energy needed to break. Okay, let's zing on. Okay, figure 6 represents the molecule C70. So zooming in a bit, this is C70. What is the name of this type of molecule? Fullerene, graphene, nanotube, or polymer? Tick 1 box. Well, it's a fullerene. In fact, the full name was Buckminster fullerene, or Bucky balls they were nicknamed as. Let's zing down a bit. Molecules such as C70 can be used in medicine to move drugs around the body. Suggest one reason why C70 molecule is suitable for this. Well, they actually act as a cage for carrying medicine. So they can actually go into your blood and carry the medicines around like a cage. We could say they're hollow. Some other possible answers are not toxic. You wouldn't want to put something poisonous in somebody's body. We wouldn't also want it to start having chemical reactions. So it's very unreactive. And all nano materials have a high surface area to volume ratio, which generally is, I would say, the most important thing to remember about nanoscience is this last one there, the high surface area to volume ratio. That will normally work its way into every answer to do with nanotechnology. All right, let's move on. Okay, let's check out 3.5. Calculate the number of C70 molecules that can be made from 1 mole of carbon atoms. So we want how many C70 molecules can we make from 1 mole of carbon atoms? Well, lots of ways to do this, but this is how many molecules are in a mole of carbon atoms. Okay, that's how many carbon atoms you get in 1 mole of carbon atoms. So we can divide that by 70, or we can do 1/70 times 6.02 times 10 to the 23. So you could do it like that, or you could just do this 6.2 times 10 to the 23 divided by 70. We know that's the amount of carbon atoms in 1 mole, and if it takes 70 to be used in a molecule of fullerene, then this is how many fullerenes you could make from 1 carbon atom. And both these answers are the same, and the answer is 8.6 times 10 to the 21. And so you're really getting, you could either do that or that, and you're getting that. I'm not really sure why it's 3 marks, so there we go. Okay, let's look at 4.1. The student adds zinc oxide to hydrochloric acid until the zinc oxide is in excess. We've heard that before with the sodium carbonate earlier. So they've added this oxide to the acid until there's no more acid and the zinc oxide is extra. They're adding extra. Give one observation the student could make to show the zinc oxide is in excess. Well, obviously, once it reacts with the acid, the solid will disappear in a neutralization reaction. But once there's no longer any acid there, you're just going to have salt and water. So adding extra zinc oxide, it won't react with the water or the salt. It's just going to float. You're going to see a solid. So see a solid, in the water, or you could say solid remaining, anything along that. You can see the solid floating in the water, sinking in the water, anything like that. Okay, it doesn't disappear. It no longer disappears. You shouldn't really say dissolves because it's not soluble, but sometimes they'll allow you to have that anyway. So let's go. Why is excess zinc oxide used rather than excess hydrochloric acid? So it's much easier afterwards. You can filter off excess zinc oxide. And then we have name one other compound the student could add to hydrochloric acid to produce zinc chloride. Well, there's lots of reactions here. If you're doing a neutralization reaction, making salts, there's 3. We could add a metal, we could add an oxide, we could add a hydroxide or a carbonate. So really we can have zinc hydroxide, we could have zinc carbonate, and you could really add zinc, but you'd make hydrogen gas. So better to add zinc hydroxide or zinc carbonate if you want a neutralization reaction. Right, 4.4. Describe how the student should obtain crystals of zinc oxide from a solution of zinc chloride. So let me just go through what's happened here. Essentially, if you look over here at this beaker, what they had at the start was hydrochloric acid. Okay, they added zinc oxide until the zinc oxide was in excess. Well, what happens when you add zinc oxide to hydrochloric acid is you end up with salt and water. So you end up with zinc chloride. I'm presuming it's zinc 2 chloride. It could be zinc 1. So we've got zinc chloride and water, and then we have our zinc oxide floating around on top, let's just say. Now they talked about us getting rid of the zinc oxide, which we do by filtering. So you can filter off the zinc oxide, and now what you've got left, once you run this through the filter, you've got zinc chloride, which is a soluble salt, and you've got that floating around in the water. So what they're asking us now is, how could we obtain crystals of zinc chloride from this zinc chloride solution? And of course, most students will say, oh, heat, and you're going to get a mark for heat the solution. You really want to heat the solution until crystals start to form, then leave it somewhere to cool and crystallize. So I'm going to kind of combine all of that. A lot of students will just say heat the solution, evaporate water. Now, they probably only give you 1 mark there because there's a technique we should do, which is a better technique, which is not just evaporate all the water. You can get side reactions. You can lose some of your zinc chloride. You want to gently heat the water, evaporate some until crystals start to form. We used to encourage this with a glass rod, but you don't have to say that anymore. So until crystals start to form, then leave to cool and crystallize. Now, this question doesn't say, how would I make sure it's pure and dry? But if you wanted it pure and dry, so if it's in a big 6 marker, I would always say refilter and dry with paper towels. Now, it doesn't say dry in the question, so you'll get no marks for that last bit. I'm just putting that there because that's something that you should know to be able to step up to and add to your answer. If it was asking for pure dry crystals of zinc chloride, then we would definitely want to crystallize it and then refilter and dry with towels. All right, coolio. Let's move on. Okay. Zinc chloride is also produced in a displacement reaction between zinc and copper chloride solution. The equation reaction is like this. Complete the Ionic equation for this reaction. This is not an electrolysis half equation. This is an Ionic equation. With Ionic equations, we only want to include things that either change their physical state or change their charge. And yeah, so what we're going to do here, the chlorine is -1 here and -1 here. So you just get rid of the chlorine. You don't need it. And what you're going to do, we write zinc, which has no charge, but the copper, when it was with the chlorine, is copper 2+. You might be like, oh, how do you know it's copper 2+? Let me go and show you. Chlorine has a charge of sugar. Chlorine has a charge of -1 because it's in group 7 and it steals electrons. So each chlorine is -1, which tells me that copper must be +2. Now, why do I not include chlorine in this reaction? And then over here, the zinc is 2+ and the copper is now on its own with no charge. And I know here that zinc must be 2+ because I still have my chlorines with it, and chlorines are -1 each. So why do we not include chlorine? In the Ionic equation, you do not include things that haven't changed their charge. So the chlorine did not change its ionic charge. It stayed as Cl- and Cl-, and in both of these it was aqueous, so it didn't change its physical state either. So at the end of the day, we call those spectator ions. You don't include them in the Ionic equation. Cool. All right, the next question, why is zinc described as being oxidized in this reaction? So hopefully you've heard of this term, oil rig. And what does oil rig mean? Well, oxidation is loss of electrons, and reduction, whoopsie, is gain or getting electrons. Okay, so oil, oxidation is loss, reduction is gain, rig. Okay, coolio. So what we need to do is look at what's happened to the zinc. Described, why is zinc described as being oxidized? Look at the zinc. What's happened to it? Zinc has gone to Zn2+. So it lost, how many electrons did it lose? It lost 2 electrons. So all we need to say is it lost 1 mark, electrons. So it lost 2 electrons. So you're getting 1 mark for saying it lost electrons and 1 mark for the 2. So it lost 2 electrons. Okay. If you just said, oh, it loses electrons, oxidation is lost, you wouldn't have even have to know about the question. Actually, it's only a 1 mark question. What am I on about? There we go. Oh, sugar. Put that back. Woo. All right, let's move on. Zinc and copper can be used with another substance to produce electricity. Okay. Complete figure 7 to show how zinc, copper, and another substance can be used to light a lamp. Zinc, copper, other substance used. Okay, the symbol represents the lamp. So we've got light. What we do with zinc and copper? Well, it looks very similar to electrolysis here, and it is a little bit like electrolysis. We're making an electrochemical cell. And how we're doing that is we're getting 2 electrodes. And because zinc and copper have different reactivities in the reactivity series, so this could be my zinc, I'm using the chemical symbols, and this is my copper, and that's going to pick me up marks for showing that I have a zinc electrode and a copper electrode. Now, I need to put them into a liquid, just like when we do electrolysis. Otherwise, electricity, I won't have a complete circuit. All right, so we want the electricity. I want the electricity to be able to flow down these metal electrodes through the solution, back up through the wires and through the lamp, and then that is going to turn my lamp on. The fact that I can have a flow of electricity. Why can I have a flow of electricity? Because zinc and copper have different reactivities. The bigger the difference in their reactivity, if I'd used copper and let's say a really reactive metal like potassium or magnesium, then I would have got a much brighter light. I'd be able to produce a lot more electrons. Now, in order for us to do this, we're going to get we need to label what's this solution. So you guys probably know the name of this solution. It's called sugar, and it's not called sugar, it's called an electrolyte. Okay, now you could name it. If I've got copper and zinc, I might want copper sulfate. I want something that is going to contain the ions basically and not react with the zinc or the copper. So we could name it if we wanted to. Cool. What are the marks here are actually for one for a liquid in a container, one for the word electrolyte, and one for the electrodes with wires attached. Okay, question 5. This question is about the periodic table. The elements in group 1 become more reactive going down the group. Rubidium is below potassium. In group 1, rubidium and potassium are added to water. Predict one observation you would see that shows rubidium is more reactive than potassium. So if something is reactive, you should know your group 1 metals, when you drop them in water, they release hydrogen. They form an alkaline and a hydrogen gas. If you're more reactive, you're going to release that hydrogen faster. And so we're going to see more bubbles. We could say more, they love this word, vigorous reaction, just like a more violent reaction. A bigger flame. You do get a lilac flame sometimes with potassium. Rubidium would burn a lot more quickly. In fact, it could even explodes, etc. There's lots of possible answers to say that you'd see a more violent reaction. Now, let's scroll down for this next one. Okay, 3 marks. This is a very common question. You either get this about group 1 or group 7. And this is the same for all metals, but at GCSE we just apply it to group 1, but it's the same for all metals. Why is rubidium more reactive than potassium? Imagine this is potassium right here, and here's its last electron. And then what's the difference with Rb, rubidium, and its last electron? Well, it's all about the distance from that positive nucleus. So what we want to say, a couple of things we want to say, rubidium is larger, has a better technical term would be Yeah, I'm just going to go rubidium is larger. You could say it has a higher atomic or a bigger atomic radius, but that's just getting too technical. So rubidium is a larger atom. There's about 5 things I'd write here, even though it's worth 3 marks. So I would say rubidium is a larger atom. So the outer electron is further from the nucleus. Now, why is that important? The nucleus is positive and electrons are negative. So if you're further from the nucleus, you're going to feel less attraction. It feels less attraction and therefore easier to remove or easier to lose electron. So it's not held as tightly, and that means that the rubidium is going to react faster than the potassium. It's going to give that electron away. Now, a little bit of extra content they normally always have on the mark scheme is that also Rb, or rubidium, has more shells. So a greater shielding effect, a bit of an A-level term that. And what does that mean? That means that the rubidium has got extra shells. Okay, if like let's say potassium is just like that, it's got less shells that are blocking that attraction to the nucleus. Rubidium has even more shells blocking the attraction to the nucleus, and of course those shells are full of electrons, so they're repelling that outer electron even further away. So there's a repulsion from the electrons don't like each other, so those shells are pushing each other further away, and there's more shells in rubidium. Anyway, these are the 3 that I would concentrate on. It's a bigger atom, electrons further from the nucleus, so it's less attracted to the nucleus, easier to remove. Okay, I've put 4 marks. I think they should give you 4, but they're stingy. There we go. Right, this is an equation you should know off by heart. It is the same for all group 1 metals. In fact, it's the same for many metals react like this, but the group 1 especially. So rubidium plus water, and this is why the group 1 metals are called alkali metals. All of them are going to form a hydroxide, which is that O, capital O and H for the oxygen and hydrogen, and they're going to give off hydrogen gas. Now we need to balance it up. So I always look to make even numbers on the right-hand side or on the left-hand side, wherever there's odd numbers. And I look here straight away and I'm like, oh, there's 1 hydrogen and 2, that's 3. That's going to be really hard to balance over here on the left. So let me make this 2 hydrogen. So we've now got 4 hydrogen in total there. Now I've got 4 hydrogen. I come back and put a 2 here, and I've also got 4 hydrogen, and then I need the 2 rubidiums, which resulted from that. And that is all balanced, 2, 2, 2. Okay, you can either learn the balancing or you could just memorize this equation off by heart. It is one of the ones you have to actually know. So you have to know this off by heart, this one, guys. All right, let's move on. Question 5.4, which is a correct statement about noble gases? Tick 1 box. The noble gases all have atoms with 8 electrons in the outer shell. The noble gases have boiling points that increase going down the group. The noble gases have molecules with 2 atoms. The noble gases react with metals to form ionic compounds. So let's go through these, and I'll go through the wrong answers. So the noble gases all have atoms with 8 electrons. Well, no, the first noble gas is helium with a mass number of 4 and only 2 protons, so only 2 electrons. So they don't all have 8 in the outer shell. So that is definitely the noble gases have boiling points that increase down the group. Of course, that's actually our correct answer. And the reason is, as we go down the group from like helium to argon, they get bigger. And being bigger, if I have like 2 argons there, the bigger you are, the more of the weak intermolecular forces they have between them. Okay, so helium's slightly smaller, and the attraction between helium is less than the attraction between argon. So with simple molecules, as you get bigger, you get stronger forces. Now, the noble gases have molecules with 2 atoms. No, they don't. They're monatomic. So that is wrong. Only the halogens are diatomic. Of course, some of the others like oxygen and nitrogen are, and hydrogen. The noble gases react with metals to form ionic compounds. You'd think they're non-metal, so they would form ionic compounds. But of course, the noble gases don't like to react. Why? Because they've got full outer shells, hence the name group 0 and not group 8. Yeah, whatever. Let's go. Figure 5.5 shows the information about 3 isotopes of neon, mass number 20, 21, 22, and the percentage abundance. Calculate the relative atomic mass of neon. Give your answer to 3 significant figures. So we've got a mass number of 20 with an abundance of 90.48. We've got a mass number of 21 with a percentage abundance of 0.27. We've got a mass number of 22 with a percentage abundance of 9.25. So all you're going to do here is do the sum of the mass numbers times the percentage abundance, add them all together, and divide by the total abundance. So you want to make sure in your calculator you put brackets in. If you don't put brackets in, if you're lazy paisy, you're going to get the wrong answer. Okay, close brackets, add that to the next one, which is a mass of 21 times 0.27, close brackets, add that to a mass of 22 times 9.25, close brackets. Oh, sugar, where did that 9 come from? That was my bracket. Now, you just want to have a quick gander and make sure the abundance is 100%. Yeah, that's going to all add up to 100%. Divide by the total abundance, which is 100. Now, make a prediction about your answer before you stick it in the calculator. So, which one is there more of? Is there more of number 20, 21, or 22? Well, there's more of number 20, which means I'm expecting the average mass of these atoms, that's what the RAM is, the average mass of the isotopes of an atom, taking into account the abundance. I'm expecting it to be very close to 20. Let's check it out. Whack it in the calculator, and we get 20.1877. Now, we don't want to lose the third mark, so give the answer to 3 sig. So what you do here is you put 3 numbers down. So we're going to go 20. The 8 is bigger than the 1, so we're going to round that to 20.2. And that's our lovely 3 marks. 1 for the working out, 1 for the answer, and 1 for rounding to 3 sig. Superbulous. Okay, question 6. This question is about electrolysis. Molten sodium chloride is electrolyzed in an industrial process to produce sodium. Figure 8 shows a simplified version of the electrolysis cell used. We've got molten sodium coming out the top here. We've got molten sodium chloride in one side and molten sodium chloride in the other side. We have chlorine gas coming out the top here. We have a positive electrode, a negative electrode, and they're separated by a porous mesh. 6.1, which is the correct half equation for the production of sodium? Sodium chloride, and they tell us in the question that it's molten. This means that it's in liquid form. It means it's been melted, and that means that the only ions that are in it are, of course, the sodium ion. Now, sodium's in group 1, so it has a +1 charge. Chlorine's in group 7 on your periodic table, so it has a minus charge. So how do we go from this, is what the question is asking us. How do we transform that to sodium? Well, we need to get rid of the plus. And of course, what that means is that sodium has lost an electron. It should have 1 in its outer shell, but of course, when it becomes an ion, this is what a sodium atom would look like once it becomes an ion. So we want to regain an electron. And so the one that represents that is going to be Na plus E minus goes to Na. So we're adding an electron back to get rid of the positive charge and turn it back into sodium atoms or sodium metal. And that's the correct answer. A mesh is used to keep the products of electrolysis apart. This is question 6.2. Suggests one reason why the products of electrolysis must be kept apart. So, what are our 2 products of electrolysis of sodium chloride, molten sodium chloride? We have chlorine gas, Cl2, and that's a gas. And then we have molten sodium. So these are our 2 products. So the whole point in splitting up sodium chloride into its ions and then reforming chlorine gas and sodium metal is so that we can use them as products. Sodium metal can be used in various chemical reactions in laboratories and things, and chlorine gas can be used in swimming pools to sterilize water and various other processes. What we don't want to happen is if we put the sodium back together with the chlorine, what's going to happen? They're just going to reform sodium chloride. So you're going to get this reaction going on. We don't want that. We've just spent a lot of money to melt the sodium chloride to make it molten, and a lot of money to separate it in the process of electrolysis. We don't want to waste all that money by returning it back to its reactant form. So the sodium and chlorine do not react to reform sodium chloride. 6.3, which type of particle passes through the mesh in the electrolysis of molten sodium chloride? Tick one box. So we're going to look at the mesh in a second. Is it the atoms, the electrons, or the ions or molecules that pass between the mesh? Well, we can work this out by actually looking at the question. So let's zing up to the diagram again. There we go. Right, so we're looking at the mesh. What's the purpose of this mesh? Why does it have holes in it? What is it that they want to allow to pass through? Well, let's have a look. We've got molten sodium chloride here and molten sodium chloride here. Now, there aren't any molecules in here because it's all sodium and chlorine ions. So you've got sodium and chlorine ions. Now, we know the chloride ions want to go there. The sodium ions need to get over to here. And over here, it says we also have molten sodium chloride, which means we also have Na+, which is fine, because that can just go here. We also have Cl- chloride ions. They need to get over here to the positive electrode where they can be discharged. So what's the reason we have holes in the mesh? It's to let ions pass through to the electrodes. Okay, so the answer here is ions. Let's move on to the next question. Aqueous sodium chloride solution is electrolyzed in a different industrial process. So not the same one. We're now dealing with a slightly different process. Two gases and an alkaline solution are produced. Which two ions are present in the aqueous sodium chloride solution in addition to sodium ions and chloride ions? Well, if we look at this, they've told us here that in this process, we have sodium chloride solution. So this is slightly different. We have NaCl, and it's got AQ. Instead of L, AQ. What that tells you, whenever you have a solution, normally in chemistry, we're dealing with water as the solvent. And in this case, the AQ symbol here, we are talking about water as a solvent. So my other two ions, other than sodium and chloride, are H+ and OH-. So the two ions present, other than the sodium ions and the chloride ions, which are over here and here, are hydrogen ions and hydroxide ions. That's what the OH- ions are. You could put the symbols or you could write the names. Now it says, name the alkaline solution produced. When you electrolyze these, there's a couple of electrolysis rules you need to know. So we've got two positive ions. So just to highlight that in red for you guys, we have sodium ions and we have hydrogen ions. Now, only one of those is going to come off at the negative electrode. So you have a negative electrode in electrolysis. We got two ions. Which one comes off? Well, it's always, if you have hydrogen present, it will always be hydrogen unless you have a less reactive metal like copper or silver. And so pretty much, unless it's copper or silver ions there, when we're dealing with any solution, absolutely any AQ, you're going to get hydrogen gases instead of metal at the negative electrode. So hydrogen has been removed. It's gone. Now, we've got two negative ions in the solution, and only one of these is going to be discharged. And the one that's going to be discharged is going to be the chloride ion. And the reason being, the chloride ion, if you have the rule of electrolysis of solutions is if you have a halide ion, which is a group 7 ion, a halogen that's become an ion, so a halide ion, like chloride ions, they will always go to the electrode. So if you have chloride, bromide, iodide, anything like that in the solution, they will always go there, and the OH will be left behind. So we can cross out the chlorine as well. The chloride ions have gone. They formed chlorine gas when they were discharged. What's that left behind? So let's look what's been left behind. And what we can see is that what's left behind are the sodium ions and the hydroxide ions. What do you think you get when you put sodium ions and hydroxide ions together? Well, the two charges cancel and they're going to form NaOH. So your answer for this is that you don't need to write this equation that I've written. You don't need to do that. You just need to write sodium hydroxide. Super. Right, going to clear that. We're going to move down to the next question. So explain, this is basically everything I've just gone through, 6.6. Explain how the alkaline solution is produced. Why did we get that alkaline solution? You should refer to the processes at the electrodes. So what we want to say is, well, H plus ions were discharged, which means lost their charge at the negative electrode. So if you don't want to say negative electrode and you want to be a bit more funky, of course, you can say cathode. That's where the positive ions go. So H plus ions were discharged at the cathode to form hydrogen. Now, you could show the equation. If you want to get real funky, you could show the equation, and that's H plus, 2H plus, picked up 2 electrons, right? And we could put a minus sign on the electrons if we like, and they form H2. It's a diatomic molecule, right? So that is our half equation, which means that there's no hydrogen ions left, okay? So we're discharged at the negative field. This removes H plus ions from solution. So I'm making mine a bit long, but I'm explaining why there's no hydrogen ions left in the solution. Then at the negative, at the positive electrode, called the anode, at the positive electrode, called the anode, if you like to use the word anode, chloride ions, Cl minus ions, are discharged to form chlorine gas. So no Cl minus left in solution, which means that all of our chlorine ions are gone. Now, if I really want to do the half equation, I'm just doing it to show you guys, but you're going to have 2 chloride ions. They're going to form chlorine gas and give back their 2 electrons, which go into the electrode, and round they go. So we've removed the hydrogen and the chlorine. And what we want to say is this leaves OH minus ions and Na positive ions, which is sodium ions, to form sodium hydroxide solution. And there we go. That is our answer for 3 marks, and that is more than the marks required. If you really want, there's some other things you could say. People find this difficult, but what happened, this will also be on the mark scheme, what happened to the hydrogen ions when they went to the negative electrode? Well, you can see here they're gaining, adding 2 electrons. Reduction is gain. So we could say, if we wanted to, H plus reduced, yeah. And if we look over here at the chloride ions, they were oxidized, they had a negative charge, and they lost the negative charge. You might remember the term oil rig. So we could say Cl minus was oxidized. Now, at this level, they won't mind if you say chlorine gas was oxidized. But yeah, chloride ions was oxidized, lost electrons. Okay, so we could add those little bits in if you really want to be extra, but that would get you all 3 marks. (7.1). The reactivity series sometimes includes non-metals such as carbon, hydrogen, and silicon. Silicon can be extracted by using silicon dioxide with different substances. The equation for one possible reaction is carbon plus silicon dioxide goes to silicon solid plus carbon monoxide gaseous. Explain what this reaction shows about the position of silicon in the reactivity series? Well, what's happened here is that the carbon over here has pushed the silicon away from the oxygen, and the carbon has taken the oxygen. So the carbon has actually been oxidized, and it's done this by reducing the silicon, by stealing its oxygen. What does that tell us about carbon? It tells us that carbon is more reactive than silicon and has displaced silicon. It is higher in the reactivity series. So what are the 2 marks for? Because there's a load of writing there. The 2 marks are mainly for you saying that the carbon has displaced silicon and carbon is more reactive. Now, you could have said silicon is less reactive, it's been displaced by the carbon. You could have worded that in different ways, but it all needs to show you really that in the reactivity series, we can tell that carbon must be above silicon because it's pushed the silicon out and stolen its oxygen over here. We can say that the silicon oxide has been reduced as it lost oxygen. Okay, let's zing on. I like to waffle a bit sometimes. Oh, I don't know what's wrong with my breathing today, but there we go. 7.2, aluminium also reduces silicon dioxide. So we could use aluminium instead. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper than aluminium. Carbon can be obtained by heating coal. Aluminium is obtained by heating aluminium oxide. Explain why aluminium is more expensive than carbon. So we've just been told here, carbon is, why is aluminium more expensive than carbon? Which is why instead of using aluminium to reduce the silicon dioxide, we use carbon because it's cheaper. They're saying, well, why is it more cheap? Well, the reason is when you heat aluminium, you need a lot more energy. And so carbon can be extracted by heating alone. Okay, so you can get carbon by heating alone. You can reduce carbon dioxide or carbon monoxide. You can get carbon anyway by just heating. Aluminium requires a lot more energy to extract. And the reason is you're going to have to, and just to go through the process, you don't need this to get the marks, but you're going to need to melt aluminium oxide. You probably remember you need that, you need cryolite to lower the melting point, but it's still fairly high, a lot of energy. You need to melt aluminium oxide. Then you need to carry out electrolysis, which uses electricity. So basically, extracting aluminium requires a lot more energy, not just heating to melt something, but you also need to use electricity to do electrolysis. So your main marks here is that carbon can be done by heating alone, aluminium requires more energy. Or you can say aluminium, you can mention electrolysis, that aluminium needs electrolysis. Cool. Let's zing, 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 zing. 7.3. Booyah. You will always get this in every exam, this type of question that's coming up now. So magnesium also reduces silicon dioxide. Magnesium is even more reactive than aluminium. The equation for the reaction is 2 magnesium solids plus silicon dioxide solid makes silicon solid plus magnesium oxide solid. Give one reason why the products are difficult to separate if magnesium is used to reduce silicon dioxide. Well, you can see what the problem is here. Look at the state symbols. So you always get a question like this, which is asking you about the state symbols. What's the problem? It's much easier to separate a gas and a solid because the gas will just rise up, be less dense than air normally and escape. It's much easier to separate a liquid and a solid because we can filter. But if you have 2 solids mixed together, it's harder to separate. So 2 solids, harder to separate. Got a bit, oh my gosh. Separate. Oh my days. Separate. So we basically need to point out here that, look, both the products are solid. That makes it harder. Okay, enough waffle. 7.4, calculate the 5 marks are going to need to move up. Calculate the minimum mass in grams of magnesium needed to completely reduce 1.2 kilograms of silicon dioxide. We've been given the relative atomic masses, which always makes you know that, allows you to know that you need to do moles, and it's worth 5 marks. So there's got some general steps for a mole equation, so let's go through it anyway. What do they want us to work out? They want us to work out the mass in grams of magnesium needed. So we need to work that out. What they have given us is 1.2 kilograms of silicon dioxide. So we now need to identify silicon dioxide. This has no oxygen with it, so that's just silicon. This is silicon and oxygen, so this is the silicon dioxide. So we have 1.2 kg of that. What is that? You should be able to work out that that is mass. And the moment in chemistry you get given a mass and you're given AR, you should be thinking of this equation, which is, of course, mass, and you should know this off by heart, over Mr. and moles. Now, I like to use a lowercase n for moles. So that's the equation we're using. So the first step, hey, let's work out how many moles of silicon dioxide we have. So how do we do that? I want to convert this into grams. Now, normally in physics and when you're dealing with mass, when you're doing physics, you always use kilograms. But in chemistry, we use grams for mass equations. So we don't use kilograms. So there's a little difference there between physics and chemistry. So we're going to turn this into grams, and that will score you 1 mark. How did I do that? I times by 1,000. Now that's given me the mass, okay, in grams, and I will now want to divide that by the MR. So let's go ahead and work out the MR for SiO2. So what is the MR of SiO2? I'm going to need 28 and 2/16. So we need to do 28 plus 16 plus 16. 32 and 28, sounds like 60. So 1200 divided by 60. I shouldn't really need my calculator for this, but always best to use your calc. And that is 20 moles. So I have 20 moles of what? Of silicon dioxide. How much magnesium would we need to completely get rid of it? This is where you've got to come to what we call the coefficients. Now, coefficients are then big numbers in balanced equations. Look there, there's a big 2 in front of Mg, but there's no number in front of SiO2. And this tells me that we have a ratio of 1 to 2 between silicon dioxide and magnesium. So for every mole of silicon dioxide I have, I need twice the amount of moles of magnesium. So I'm going to do 20N times 2, and that means I need 40 moles of magnesium. But this should have got you 4 marks by now. 1 for the conversion over here. 1 for working out your MR, potentially, probably not. 1 for the moles there, 1 for the ratio. And now what we need to do is it's asked for mass, not moles. So calculate the minimum mass in grams. So we need to convert that. And how do we do that? Well, we take 40N going over here. 40N is our moles. We've got to multiply that by the MR of magnesium, which is 24. So 40N times 24. And bust out the calculator. Let's have a little look. So we want to go 40 times 24 equals 960 grams. And that is our final lovely jubbly answer. Now, Si2H6 is a covalent compound of silicon and hydrogen. 7.5, complete figure 9 to show the outer shell electrons in a molecule of Si2H6. So what we need to do here is check how many outer electrons are in each of these. And if we go to our periodic table, silicon is in group 4. So I want 4 electrons from silicon. I'm going to put them all on the line there. And I want 4 electrons from the other silicon. I can use a different color, which is lovely. Which is nice. Okay, so there's silicon's electrons. and that each one has 4. So wonderful. Now what I want to do is put hydrogen's electrons on. I'm going to use a cross for these, for the hydrogen ones. Oh, better not to use the same color green. I was trying to use a different color there. All right, so we've got hydrogen's electrons. And there we go. What you need to do next is check that each one has 8. So you take your finger and you go 1, 2, 3, 4, 5, 6, 7, 8. That silicon is happy. 1, 2, 3, 4, 5, 6, 7, 8. That silicon is happy. Now we check hydrogen. It's only got an inner shell, the smallest shell. It only needs 2. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Boom. Very happy. Let's go. All right, guys, let's move on. Okay, this is a 4-mark question. 7.6. Si2H6 reacts with oxygen. The equation for the reaction is 2 Si2H6 in gaseous form plus 7 oxygen molecules in gaseous form forms 4 silicon oxides solid plus 6 H2O in gaseous form. 30 centimeters of Si2H6 is reacted with 150 centimeters an excess of oxygen. Calculate the total volume of gases present after the reaction. All volumes of gases are measured at the same temperature and pressure. Now this is key. When they're measured at the same temperature and pressure, what does this actually tell me? This tells me that basically volume is equal to moles at this point. So this is really important. This tells me that 1 mole of any gas is equal to 24,000 centimeter cubed, or if you like, 24 decimeter cubed. And that's what it tells me when you have the same temperature and pressure. So, okay, this tells me that 1 mole of any gas is equal to 24,000 centimeter cubed or 24 decimeters. Now, what we want to do here is show that, look, oxygen is in excess, which means some is left over. So with our oxygen, we've got some left over. Okay, even though it's a reactant, it means some of this is left over. Now over here, we have 30 centimeters of this one. However, all used up. So none of that 30 centimeters is going to be left. So what do? But we use that 30 centimeters to work out how much of the oxygen gets used up. They react in a 2:7 ratio. So the reaction between these two is 2:7. So what I need to do is take 30, times it by 3.5, boom, boom, boom. 30 times 3.5 equals 105. Okay, I could times it by 3.5. What am I on about? I'm on about 2/7. Okay, and that equals 105. So we know that 105 centimeters of oxygen got used up, right? Okay, how much was left? Well, they told us there was 150 centimeters of oxygen, didn't they? And they said it was in excess. They said there'd be extra. So what we want to do is 150 centimeter cubed minus 105 centimeter cubed, and that is going to equal 45 centimeter cubed of O2 left. So is the answer 45? No, but we would have scored a couple of marks for working out the leftover oxygen. But it's not just oxygen that's the gas that's left over. It wants the total volume of gases. Now, you could make the mistake to think you need to do silicon dioxide, but you don't, because solid, not gas. This is a solid, not a gas, so it's not included. However, this water has come off as a water vapor, and the coefficient is 2:6. So we have a ratio between water and Si, this horrible Si H2, oh my gosh, I can't even write anymore. Si2H6 is in a ratio with the H2O of 2 to 6. So we have 30 of that. How much are we going to have of that? Well, of course, that's the same as saying a 1 to 3 ratio. So we need to times it by 3. And we're going to have 90 centimeters cubed of H2O. Now let's work out that total. So we're going to go 90 of H2O plus the 45 of oxygen that was in excess. And we're going to get a total of 135 centimeter cubed left over. We've got none of this because it wasn't in excess, and we've got none of this because it was solid. We know that we have 45 of that left because 105 was used out of 150, and we know that we had 3 times the amount of this formed because the ratio is 2 to 6 or 1 to 3. Okay, 8. This question is about acids and alkalis. 8.1. Explain why the pH of an acid depends on the strength of the acid and the concentration of the acid. Well, what is pH? So start off with your definition of pH. pH is a measure of the number of protons, or the proton or hydrogen ion concentration in the solution. So what is pH? We started off with that, and that will get us 1 mark. We're just explaining that the pH is the measure of hydrogen ions in a solution. So that's going to get you a mark just to explain what we're going on about. And what does that mean? That means the higher the hydrogen ion concentration, God, I have trouble with that word, the lower the pH. So that could get us another mark, really. Just explaining what pH is and how hydrogen ion concentration relates to the pH. Now, we need to focus to grab our next 2 marks. We need to really focus on these 2 factors. First of all, the strength of the acid. So what's the strength of an acid got to do with the hydrogen ion concentration and therefore the pH? Well, let's look at the strength of an acid. The stronger an acid is, the more fully it ionizes. Oh my gosh, I can't even write. Ionizes. So just for those of you that don't know what that means that strong acids fully ionize in solution, and therefore the stronger the acid, the more fully it ionizes, the more hydrogen ions it will release, the more H plus ions it will release. Okay, so that all relates, I give myself 4 marks already. Okay, that all relates back to what the question is asking us is, why does the pH of a solution depend on the strength of an acid? We've explained, well, pH is the measure of the hydrogen ion concentration in the solution. And if you have a high hydrogen ion concentration, you're going to have a low pH. So if you have a strong acid, it's going to fully ionize, meaning you've got lots of hydrogen ions, therefore a lower pH. We could do the opposite and say if you have a weaker acid, it will only partially ionize, less hydrogen ions, therefore a higher pH. We could have said that. Now we want to focus on how does the concentration of the acid matter? Well, you could say lower here or higher, but I'm arguing with the higher. So the higher the concentration of the acid, the more acid is in the same volume. So if I have a 1 mole per decimeter, then that's going to have more acid than something that has a 0.5 mole per decimeter, which will only have half the amount of acid in a decimeter in the same volume. So the higher the concentration of the acid, the more acid is in the same volume. And just for those of you that are wondering what the fudge does that mean, oh my good gosh, right, what we're basically saying is if I have 1 mole of my hydrochloric acid, let's say, in a decimeter, then the concentration is 1 mole per decimeter. That means I've got more hydrogen ions than I would have if we use the same decimeter, same liter or decimeter, if I only put half a mole or 0.5 mole. So if I only put half the amount of hydrochloric acid in there, I'm only going to have half the hydrogen ions. So the higher the concentration of the acid, the more acid is in the same volume. We can follow that up by saying, therefore, the higher the conc, the lower the pH, which I kind of already said up and above there. If you noticed, I already said that there, so I'm just kind of repeating myself there a bit. But yeah, you need 4 of those points to get your 4 marks. Right. 8.2. A student titrated 25 centimeter cubed of hydrochloric acid with 0.1 mole per decimeter cubed of barium hydroxide solution. Table 2 shows the results. Here's table 2. Titration number 1, 2, 3, 4, 5. They've done 5 titrations. Volume of barium hydroxide solution used in centimeter cubed, we've got 23.90 for the first titration, then 23.45, 23.55, 23.55, and finally another 23.45. The student calculated the volume of barium hydroxide solution to be used in the titration calculation must be 23.50. Explain why the student used a volume of 23.50 of barium hydroxide solution in the titration calculation. Well, what we want to do here, what you've got to do with calculations is look for concordant results. And they've got to be within 0.1 or 0.2, depending on which exam board you're studying, of each other. They've got to be concordant. And for AQA, I believe it's 0.1 decimeters, 0.1 centimeter cubed, they've got to be within. So you can see that these 4 results are all concordant. They're all within 0.1 centimeter cubed. This one is not to be used. So there's many ways to get the 2 marks here. We could say 23.90 is anomalous. We could say 23.90 is anomalous or non-concordant. So it's up to you. But you could say, yeah, can't use that one. Results 2 to 5, the ones I've circled there, are concordant within 0.1 centimeter cubed of each other and should be used in the mean calculation. So when calculating, I'm going to take 23.45, add it to 23.55, add it to 23.55, add it to 23.45, and I'm going to divide by 4. So we've excluded the anomalous result, and that's the explanation you need to get you the marks. Nice fat titration calculation. We love one of them. 8.3. 25 centimeter cubed of hydrochloric acid reacted with 23.50 centimeter cubed of 0.100 mole per decimeter of barium hydroxide solution. The equation for the reaction is 2HCl aqueous plus BaOH2 aqueous goes to BaCl2 aqueous plus 2H2O liquid. Calculate the concentration of the hydrochloric acid in moles per decimeter.
Stick around. I'm going to have to science the shit out of this.
So the first thing you need, if you want to solve this, you're totally screwed if you haven't memorized your chemistry calculation. And don't be stupid and think, oh, they might give it to us in the exam. They're not going to give it to you in the exam because there's no equation sheet for chemistry, and there never has been. So we've got number of moles over concentration times volume. You need to know that off by heart. Now, another little factor to remember is that volume is always in decimeter cubed, concentration is in mole dm cubed. So the thing to do is to work out what your first part is, right? We know we've got 25 centimeter cubed, that's a volume of HCl. But over here, you can see that reacted with 23.50, that's a volume of 0.1 mole per decimeter. That's not moles, that's not N, that's concentration, and that's a barium hydroxide. So the first thing we can do, we need to work out the concentration of hydrochloric acid, but we have the C and the V for the barium hydroxide. So let's work out our moles of barium hydroxide, and we can do that by, here it is. What we're going to do is do C times V. And the C is 0.100 and the V is 23.50. But we have a problem. This is centimeter cubed and this is in mole per decimeter cubed, right? So the units for volume in each of these do not match. So I need to divide this by 1,000. So it's the same thing as going 0. And what you can do with these titrations is just add 2 zeros to the centimeters rather than bothering to divide, because and then you get 0.02350, and we change that to decimeters. So now multiply those together and we're going to get N for BA, yikes, OH2. So we've got the barium hydroxide moles, and the moles of barium hydroxide going to be 0.00235. So that's 0.00235, or 2.35 times 10 to the minus 3 on your calculator, but that's essentially what it equals. Now what we need to do is look at the ratio. We need to find out what the moles of hydrochloric acid are. So let's get off this nasty color and go up here. Here's barium hydroxide. It has no coefficient in front of it, so we can just assume it's 1. And the hydrochloric acid has a 2. So for every barium hydroxide molecule that reacts in a neutralization reaction, it's going to need 2 hydrochloric acids. So if I want to find the moles of hydrochloric acid, I'm going to times my barium hydroxide by 2 to get the hydrochloric acid moles. So the ratio is 2 to 1. So I'm going to go 2 times 0.00235, and that is going to give me my moles of hydrochloric acid. And I'm now up to scoring myself 3 marks, because that is going to be double that. That's going to be 0.00470. And that is my moles of hydrochloric acid. So you've now secured yourself 1 for converting that, 1 for timesing that, 1 for using the ratio. So we've now got 3 lovely jubbly marks. What we want to do now is get that final mark. And how are we going to get the final mark? So the final mark, the question didn't ask us for the moles of hydrochloric acid. It asked for the concentration. So we need to pop our stuff back in here. And what we're going to focus on is moles over volume gives me my concentration. So the moles of hydrochloric acid were 0.00470. You divide that by the volume of hydrochloric acid, which is up here. We identified it was 25. We have an issue. We got to turn it into decimeters. So we just add 2 zeros and divide it by 0.025. Okay, you really divide by 1,000, use your calculator, but that's my shorthand way, is just to whack 2 zeros in the front. And the final answer that gets you the final mark is 0.188. And that's the concentration. So I want the units, which is mole dm 3, and I should put a line through it, although at A level we don't put a line in between, we just write to the minus 3. Okay, have I got all of this question up here? No. The equation for the reaction is H2SO4 aqueous, sulfuric acid, plus barium hydroxide BaOH2 aqueous, goes to barium sulfate BaSO4 solid, plus 2H2O liquid. When they give you these state symbols, they often play an important role in the question. The student measured the electrical conductivity of the mixture during the titration. The better a conductor, the higher the electrical conductor value. Figure 10 shows the results. So what we're going to do here is have a look at this little crummy graph, although we don't need it too much for this question. Electrical conductivity in arbitrary units. What does that mean, AU? That means just random units, like you don't need to worry about the unit. It's just like a standardized for the electrical conductivity. So we've got 2.6 when the volume of barium hydroxide solution added in centimeter cubed is 0. However, once we get to adding 30 centimeters or nearly 30 centimeters of barium hydroxide solution, then the electrical conductivity falls to 0. It will no longer conduct electricity. Let's get a look at this question further. 3 marker. Lovely bubbly. Okay. 8.4. Explain why the electrical conductivity of the mixture was 0 when the sulfuric acid has been neutralized. Use the equation for the reaction. Refer to ions in your answer. Now, if we go up here, and they're talking about ions. So if we go up here and look at this equation, look at the products. When we have completed neutralization exactly, and we don't have any leftover barium hydroxide or any sulfuric acid that are both aqueous, we will just be left with the products, which are solid barium sulfate, which is ionic. However, it's locked in an ionic lattice where the ions are not free to move. It's insoluble. And we have water, which is a simple covalent molecule and has no free ions, so does not conduct electricity. Don't think that the water in your house won't, because that's not pure water. The water in your house has dissolved ions in it, and so it is dangerous. The water on the earth is dangerous. It has dissolved ions in it. But if you have deionized water or distilled water, that should not conduct electricity because it's a simple covalent molecule. Right. Let's get on it and write this answer down. So refer to ions. Basically, barium sulfate is a solid, no free ions able to move. So basically, it doesn't have any ions that can move. If it was melted barium sulfate, that's a different story. The ions would be free to move and carry charge. However, not here. H2O is a simple covalent substance or molecule or compound. So no ions or no free ions. In fact, it's got no free ions or delocalized electrons to carry charge. And really and truly, yeah, the only way that anything in chemistry can conduct electricity, you have to have one or two things. You either have free moving ions, which you get if you're an ionic compound that's been melted or dissolved in aqueous solution, or you have delocalized electrons like metals or graphite. Water is a simple covalent substance. It has neither free ions or delocalized electrons. And barium sulfate does have ions, but they're not free when it's in the solid form. Okay, coolio. Let's move on. Last question, 8.5. The student added a further 10 centimeter cubed of barium hydroxide solution. The electrical conductivity of the mixture increased. Give a reason why. Well, remember, we only have barium sulfate and water in the products in the equation above. Now we've just added a solution of barium hydroxide. It's an ionic compound and it's in solution. So guess what? It's got free ions. So we'd say barium hydroxide, forget all the caps, and that solution has free ions. Okay, now what are we on about? Well, barium, it's got 2+ ions. Hydroxide has OH- hydroxide ions. These are now able to carry charge. So yeah, boom. If you're looking at water, why can water not carry charge? Well, it's made up of these bad boys. So it is made up of ions, but they get together to form H2O. So that, in theory, is why water, liquid water, doesn't conduct electricity if it's pure water. But yeah, it's another story. Right, cool. Thanks for watching. Like, subscribe, check out my other videos, add some comments, put some recommendations. Let's go get those GCSEs.
You still here? It's over.